Thank you for your patience, guys. Finally found a technical problem. And welcome you all once again for the May chance meeting. First of all, the student presentation is going to presented by Yasid Kanchanalokige on the topic Introduction to Eagle-Bone Embedded Hardware.
Good afternoon, everybody. I am Yasid Kanchanalokige. I am from University of Columbus School of Computing. Since you all are software experts, I decided to do my presentation on Beagle-Bone Embedded Hardware. Today's topic is Introduction to Beagle-Bone Embedded Hardware. You might have probably heard of Beagle-Bone. So what is Beagle-Bone? Beagle-Bone is a credit card size small microcomputer. As you can see here, it's very small credit card size microcomputer. It's completely open source and runs many open source softwares. Open source operating systems, and it's low in price. It's about $89 US. It has internet connectivity, runs multiple operating systems, as I told you. There are plenty of input and output ports. As you can see here, these black ports are input-output ports, and it has higher processing power. The processor is AM335X, 720 MHz. ARM Cortex A8 processor. As I told you, processor is ARM Cortex A8 processor, and it has inbuilt 3D graphic accelerator. When you talk about connectivity, it has two USB ports, USB client and USB host. You can power it up using USB port, and there are 92 pin headers. As you can see here, those black pin headers are GPIO ports, and 7 analog digital converters, 66 general purpose input output ports, 2 inter-integrated circuit ports, 5 UART. UART means universal synchronous receiver transmitter, means serial port, SPI serial peripheral interface, CAN port means control area network port, 8 PWM ports. PWM means pulse width modulation ports, and you can connect LCD panel to this little thing and parallel connect many things. And there's a micro SD card reader here. You can store any data in this micro SD card. And when we talk about Beagle family, there are 3 members: Beagle-Bone, this one, and Beagle-Bone Black is the latest one. The Beagle-Bone Black is the competitor to Raspberry Pi, and Beagle-Board is the big brother. He's quite bigger than Beagle-Bone. As I told you, Beagle-Bone Black is the latest one. It has 1 GHz ARM Cortex A8 processor, microprocessor, and 512 MB of DDR3 RAM. And it has Ethernet port, USB host connectivity. You can connect mouse, keyboard, webcam, anything. Micro HDMI port, you can connect it to the TV or monitor, and micro SD connector. 512 MB of DDR3 RAM. And it also have expansion headers, 65 digital input output, 7 analog ports, 4 serial ports, 2 serial peripheral interface ports, and 2 inter-integrated circuits, and 8 PWM ports, 4 timers. And it has 1 GHz Citara AM335X ARM Cortex A8 processor. This is Beagle-Board. This is the big brother of Beagle family. It's 1 GHz, quite powerful than Beagle-Bone, and 512 MB of low power DDR RAM. These are the operating systems you can run on Beagle-Bone: Angstrom Linux, Ubuntu, Android 4.0. You can run Ice Cream Sandwich on Beagle-Bone, and Debian, Fedora, and above all, you can run Microsoft Windows embedded on Beagle-Bone. You can run C++, C programs on Beagle-Bone, and Java development. You can do Java development in Beagle-Bone, and Python, And also you can install OpenCV libraries to BeagleBone, and you can connect a webcam and do some face recognition of things using this little microprocessor. When you talk about applications, the main application is robotics. I designed a robot to demonstrate the basic functions of BeagleBone, so I need some time to set it up. You can connect to the BeagleBone using terminal. Right now this BeagleBone is running Angstrom Linux, as you can see here. Default login is root. Now we are connected to the BeagleBone. This robot is designed to be controlled by mobile using mobile phone. As you can see here, it can be controlled by Android app I use here. It can also control from this mobile phone. Right now I am having a technical difficulty. The basic function of this program is like basic architecture is like this. The router connects laptop and smartphone and BeagleBone together. There's a file in localhost. What I am doing using this mobile phone is changing some values in that file in the localhost. So BeagleBone also can access that file. It gets the information of that file and do according to the instructions. So like forward, turn left, turn right, and reverse. Those are the instructions. It do things according to those instructions. Architecture of the software board is like this. First I configure the pins, general purpose input output pins using those functions. First you have to export pins, then you have to set the direction of pins, whether it is an input or it is an output. Then there's a function get value. You can have the value of whether it is 1 or 0. Or you can set the value to high or low conditions. Then I/O configuration, input-output configuration is done in that part. That robot control part is basically the moving of the robot, move forward, turn left, turn right, and stop functions are described there. If you are interested in BeagleBoard, you can refer those links, beagleboard.org. If you have any questions, please raise your hand.
I have a question that you told that the OS is running on a BeagleBoard.
Yeah.
And are they specially designed for only BeagleBoard, or we can use the normal operating system distros like Ubuntu?
No, you can't use those normal operating systems. They are specially designed for BeagleBoard. You can have it from BeagleBoard website. Any questions?
So you have to connect the Wi-Fi separate for to this robot, like the BeagleBone doesn't support Wi-Fi.
I think some people have told me that BeagleBone also support Wi-Fi using that Wi-Fi module, USB Wi-Fi module. But here I am using mobile phone to connect to the Wi-Fi. You can use mobile phone and then USB tethering in Android phones. You can connect Android mobile phone and have Wi-Fi connection.
That means that same thing that you can do with the Wi-Fi rather than connecting to a USB.
Yeah. You can also connect Ethernet cable and directly connect to the internet. Any questions? Okay, thank you very much.
Anyone notice this is legal bond or not?
If anyone need to try it out, you can come here.
So now it's running without that Apache server, right?
No, it's running on local host. Yeah. The file is in the local host. This.
So to work the current situation, you need that server
Yeah.
to connect through Wi-Fi.
This is not connected through the wire. What I'm doing.
Laptop, you start the Apache server and connect to this Wi-Fi router.
Yeah.
So now it's connected.
Now it's connected to the server through the mobile phone. What I'm doing here is not directly giving instructions to the BeagleBone. What I'm doing here is changing some values in the file at the local host. He can access local host through this phone, mobile phone.
So now you're using that phone as just an input device, not that processing device.
Yeah, just as input device. Only to connect to the internet, I'm using mobile phone. I'm not directly giving the instructions to the BeagleBone. What I'm doing is changing some values in the file at the local host.
Anyone who needs to try it out?
Anyone needs to check this out? This is BeagleBone.
Thank you very much, Rasid, for your interesting demo on BeagleBone embedded hardware. Now it's the time for the industrial presentation by Dr. Umesh Ramana, Managing Director of Sim-Centric Technologies Private Limited. His topic will be simulation, evolution, and current state of the art. I think it will be an interesting one as well. So guys, enjoy that presentation. Dr. Umesh, take this one.
Okay. Good afternoon, everybody. My name is Umesh Ramana. As you can see, I'm the Managing Director and, more importantly, the CTO of Sim-Centric Technology. We are a Sri Lankan-based company. We have about 90 employees. We are based just down the road in Kolkata. And we develop simulators. We develop individual simulation training applications. And we also develop other applications which are used as add-ons or complements to existing simulation software. So what I'm going to do today is I'm going to just give you a brief introduction to what simulation technology is, because the common perception among people when you talk about simulations is that simulations are all about aircraft simulators. What I'm going to show you today is that the whole simulation industry has changed hugely and is actually now one of the hottest fields in the world. I go for conferences around the world and trade shows, and the typical trade shows that you have for simulations now have about 100, 200 companies participating in each simulation show, selling simulations to companies, governments, militaries, all that. And in each conference, you have billions and billions of dollars of sales being made. And the typical simulation industry now is worth about $20 billion, which is about 5 times the size of the Sri Lankan economy. So it's a huge field. But the thing is, at the moment, simulation industry is very, very specialized. And you only have like 100, 150 companies around the world developing the software. And in Sri Lanka, as far as I know, we are the only company to develop software of this type. And also in the whole of Asia, we only know of one company in India who does simulations, but even they only develop software for the Indian Army. So we are actually one of the more unique companies in the whole of Asia where we develop software. And our software is now currently used by the US government, the US Army, the US Marine Corps, the US Navy, the UK MOD, NATO, France, Germany, you name it, our software is used by all these companies. So to start off with, just I've broken down my talk in 5 sections. I'll give you a brief introduction to simulations. I'll talk about why things have changed, what's different about now. And then I'll take you through several examples. That's the interesting part of my talk. We got lots of videos and lots of demonstrations on simulations being used around the world. And then I'll move on to talk a little bit about our company And I'll give you some demos of the software that we develop and we are marketing and are being used by clients around the world. And then I'll finish off by giving you a very brief introduction on if you would build your own simulation, what are the basic steps that you need to follow if you would build something that's world class or something that you can actually sell to someone. Okay. So we start off with a history of simulation. So very basically, a simulation is basically a model of a real world process, something that happens in the real world. You try to model it, and if it's a computer-based simulation, you try to model it or you try to recreate what happens in the real world on a computer. And it could be anything from a flight simulator to simulating a rocket to simulating a city, but I'll give you lots and lots of examples of this. So it all started, surprisingly, in the 1920s. We had this guy called Edward Link, and he developed this thing called the Link pilot trainer. Very, very simple, as you can see here. It was all built with hardware. For every single type of flight, every single type of training that they did, as you see from this video. It was all about training the pilot to fly blind, but there was no computer. There were no computers at the time, and there would be somebody outside basically doing what the plane should be doing, and it was all very, very crude. But this was the first flight simulator ever built, and this was a start. And very surprisingly, this was all the way in the 1920s. And the company that developed this, or the person who developed this bit of kit, Edward Link, he founded a company called L3, and is actually now one of the largest simulator companies in the world, and builds simulators for Airbus and Boeing, still done by the same company. Okay. So then things changed slightly. The big change happened with World War II. There were lots of different planes. So then money started being pumped into simulation industry. And then we had more and more specific simulators being built for some of the large bombers, for some of the smaller bombers, like that. There were a lot. But once again, all this stuff was hardware-based. And the first big change came in the 1950s when computers first came out. For the first time, people were able to link simulators to computers. And then all of these complex calculations, the things that the guy was seated outside doing certain things, it was possible to do all that with a computer. And then in the 1950s, we had better flight simulators. You had a project called Project Whirlwind, which developed a very, very complex computer. And this computer was the first computer used in simulators. And they built very specific, much more complex simulators using the computer hardware. Because you were able to actually simulate and try and experiment or give details on how that exact plane looks and how that exact plane feels. There were still no visuals, but this is how it worked. And then in the 1960s was the big change. And the big change during that time was the missions to the moon, where NASA spent a lot of money on building their shuttles, their rockets, their experiments. And NASA built this huge simulator to basically simulate all the Apollo missions, the astronauts who were going into space. On this simulator, they could simulate everything that they would do in a mission, right from the start where they step into the rocket on Earth, and then go all the way to the moon, do whatever they do, and then come back. They basically figured out ways, and this simulator probably cost more than as much as the entire project. But they built an entire, and once again, this was all hardware based. And during this time, they also came out with small tricks to give visuals as well, so that you can see what's going on. And one of the tricks that they used was they took a huge photograph of a big map of the area that they're training, and then you had this camera which was just moving all over the place. And then inside the simulator, you would see the map where you're seeing or where you're at that point. And this was just the way the simulator started. And then in the 1970s, computers became a bit more complex. And we had better CGI systems, computer-generated graphics. And as you can see, we had better flight simulators, things that are coming in. But of course, the huge change, the big change that came with simulators was with the advent of the personal computer. In 1980, instead of having computers which fill the room this size, what we had was a small computer like this, which was very cheap, and then more and more people could afford to buy these computers. And also processing power, memory, everything became much cheaper. So simulators now became available to not only the rich airlines or the rich military, you could suddenly start building simulations for slightly smaller companies instead. And then, what was the really big change in simulation technology was gaming technology, surprisingly. It was actually the advent of games, computer games, which has really brought simulations up to the level where we are now, and I'll explain why. So, if you just look at the evolution of computer games, starting from the 1970s, we have games like this, going over like end of early 1990s, we had pretty good graphics along this sort. And then, when we got to the 90s and the 2000s, games became really realistic. I mean, once you're in the game environment, there was, I mean, the graphics were good, the physics was good, the models were good. Things just became better. And the main reason for this is that the gaming industry is huge. The gaming industry is something like a $50 billion industry annually. And that's about 2 times the amount of the entire film industry in the world. That's how big the gaming industry is. There's lots and lots of money going into games, which means that the people who work in these gaming companies have lots of money to research. They can build better physics models, better chemistry models, all that. So, because of that, games basically went from what I showed you earlier to this within a very short period of time, about 10 years. And now, because gaming technology is at such a good level, simulations now take whatever they can from games and just build the extra stuff that they need for simulation. Suddenly we have really good simulations which can be used for many different purposes. I'll show you examples of that. Okay? So like I said, the gaming industry is huge. It's an enormous industry. It's much bigger than almost the entire entertainment industry in the world. The gaming industry overshadows that because the amount of gaming consoles, games, and the money being spent on games is enormous. Right, so because of that, what we have. So basically what's different now? So the main difference is that now with simulations and simulators, with better systems, you can do lots and lots of things. One thing that you can do is you can model natural systems like weather systems, planetary systems, things like that. You can do performance optimization. You can take something that's already done in a certain way, simulate it, and then figure out a better way to do it. And I'll show you some examples of it. You can do engineering, safety engineering. You can be making this building safer. You can be making a car safer. You can be making a road safer, a junction safer, whatever. All can be done. You can do testing. You can do training, and you can also do a lot of education, and that's what I'm mainly going to talk about, which is simulations in training, how simulations are used for training purposes. So why use simulations? Obviously, cost, right? It's much cheaper to run something on a computer, try it out many times, and actually want to go out there and do it yourself, because it takes time, it takes money, it takes people, and whereas with the computer you can do the same thing over and over again as many times as you want, with small changes, and obviously you get better results. Time, it's much faster to run a computer. Flexibility, you can do it in a particular way and then change something. You're testing the safety of this room. You put the door there, see how safe it is. Put another door here, see how safe it is. You can do the same thing over and over again with different parameters. You can easily configure it, like so you can add things really fast. You can reuse it as much as you want. And you can also collect data much easier than you would be able to do it in the real world. You can control it, you can take it anywhere you would like, and also, because computers are so powerful, you can run huge simulations, long runs, on just a laptop like this. So, haven't simulations been around for a long time? Yes, like I said, they've been used for the last 90 years now. But it's only in the last 20 years or so that civil society suddenly realized that simulations are useful to them as well. Earlier it was mainly in the airline industry, and a little bit of military, which was using simulations. But now, like I said, because of gaming, PCs, those two things together, there's more and more technology available to do better simulations, and they're becoming more and more useful to people. So, cost of computers, and like I said, this really is one of the biggest boom fields in the world at the moment. But unfortunately, that culture still hasn't come into Sri Lanka. Those subjects are not being taught in universities. So I'm hoping that these things will change over the next few years. Because like I said, this really is a multi-billion-dollar industry, and for a country like Sri Lanka, it's very applicable. There's so many things that we can work on, from architecture to buildings to city planning to road safety. Everything can be modeled properly, and things can be improved if people are developing good simulations for our own purpose. Right? And then this is something slightly different, but another reason for simulations being very popular around the world is around the 1980s. The military got together and defined a new protocol called DIS. It's called the distributive interactive simulations. And this basically allows simulators of different types to talk to each other. Now earlier, if you had to do a helicopter simulation, then all you could do was play around with the helicopter. If you want to do a ship simulation, then you had a ship simulator, you could drive the ship around, but that's it. But then what if you want to do a joint exercise? The army wanted to do a joint exercise with the Navy, Air Force, the helicopters, the people all joining in to do a joint mission. So this is like it's a protocol, it's like TCP/IP. It allows different simulators to talk to each other and display each other's information. So using this US Army does this every day, where they have one helicopter simulator, then they have like 3 or 4 people on helicopter simulators, they have another 100 troops on normal ground troop simulators, somebody on ship simulators, another guys on helicopter, and they all join together on the same mission. And the guy who's flying helicopter flies helicopter, and the guy on the ground, when the helicopter actually flies over him, on his simulation, he can see the helicopter flying over him in real time. And that allows different simulations to come together, and you can do more and more complex simulations and tests while you do that. Okay? Alright, so this is the interesting part of my talk, where I'll actually show you some examples of recent use of simulations. So, the main thing with simulations is, before you do anything, what you need is a good model, right? You need a good model. Whatever you build has to be as close to what happens in the real world as possible. If not, the simulation is not of use to anybody. Simulations can be nice to do a video or a singer, but we are talking about using things for proper purposes. And if your simulation is going to be useful to anybody, it's got to be realistic. So the first thing you've got to do is build a good model. So I'm going to concentrate on crowd models. So if you have a good crowd model, what you can do is you can model a very, very complex scenario, like this is a very dense, compact trade show. And if your model is good enough, then you can simulate the way that people walk through this. Right? Similarly, if your model is good enough, you can also simulate outdoor spaces. Like this is a refugee camp in Somalia, and they try to use the same model to see if you can simulate people inside that area and see if and this is the real world, this is the real shot, and they compare to see whether the computer generated model is actually similar to this or not. Right? And then another example that I got is in my car. This is once again a real shot, and then a computer generated shot to see whether this is similar. This is speeded up 3 times, so people don't actually move this fast. But once again, this is I think something like 1,000 people in this area, and computer model is good enough to be able to simulate such a large code at once. Now, once you have a model like this, the things that you can do with that model are huge, right? The amount of things you can do. One of the things you can do is planning. Now, you can do what's called safety evacuation. Now, I've got this trade flow or shopping center or whatever. I've got people walking around. I want to see whether this building is safe. If an explosion or a bomb or something goes off here, how safe is the building? How fast can people get out? Right? Or similarly, I can test if there's a bomb goes off here, how long is it going to take for people to get out? And like that, before you build it, if you can make the additions, you can then decide how many doors do I need, or why should the corridors be, how can I bring the building up to level where everybody can evacuate, say within 2 minutes time. So this, once you have the model, it's then very easy to do models like this. Once the explosion happens, you see how fast the people can get out of it, right? Similarly, like this, the more complex your model is, you can do even more complex evaluations like a full stadium, and actually see how safe the stadium is as well. You can build full 3D models and use this to see what you can do to improve the safety of your building. Now, the model that you use or the visuals that you use don't necessarily have to be all that funky. I mean, you would only do what you need to do for the purpose that you're trying to achieve. So if I'm like modeling a school and I need to see how long it takes to evacuate everybody, I really don't need very, very complex graphics. All I need is a good underlying physics and cloud about this model. And then I can do the same thing with a simulation like this. So once again, a fire happens here, and they're going to see how long it takes to evacuate everybody out of this building. And then using this model, they can then decide whether you need extra doors, extra exits, whether this corridor should be a bit wider, the door should be wider. You can just test out different things to see what works better. And it doesn't really cost you anything once it's built, because it's all on a computer and it's a reusable model. Alright? So evacuation model, like I said, is one example. Another example is if you want to do crowd control planning. Now, this is a typical airport with the security check-ins, and you're trying to see how you can control the crowds. You can set up this zigzag setup. So, similarly, you can use this simulation to see how your setup will work when you have a little bit of people coming in, or if you have a very crowded situation. Can this still deal with it? Do you need more stalls here? Do you need this to be wider here? Does it have to be narrower? It's all decisions that you can make before you actually go and do it. But it all once again depends on how good your model is. If your model is bad, this is not going to be good, right? Something else I can do, similarly, moving away from crowds, you can do planning, like I said. Before you do something, you try to see whether the decisions you made have been correct. So like that, you can do, for example, you're building a new part of the city, you're trying to figure out how the road should be, how the junction should be, how the buildings, how many parks. And like that, you can model an entire city. And you go into as much detail as you want it to go into. So it could be a very simple wireframe model like this, or you can actually model the roads and actually put some cars. The cars can be dots like this, or you can actually represent real cars. It just all depends on the level of detail that you need for what you are trying to achieve. Okay. And then once you have a model like this, then you can decide where do you need traffic lights, how wide should the road be, where should pedestrian crossing be, and actually you just walk around the city and see how it looks like before you actually build it. Alright. Similarly, also doing planning, another thing that simulations are used quite extensively for is optimization of processes. Something that is happening in a certain way, you want to see whether you can improve the way that it happens. So these are typical cars, and I can see there are 4 robots here, that's kind of where they're going. And then using the simulation, show a good model of how this exactly works. You can then do a model and say, right, what if I increase this number of robots, I have 6 robots here. Can I do more cars per hour or per day? Right? Or can I make the conveyor belt move faster? Can I get the same speed by using less robots? So all these simulations you can try out before you actually buy stuff, before you do anything. It allows you to do that. Similarly, instead of doing only a section of something, you can do an entire factory. You can model the entire factory before you actually build it and figure out what's the equipment you want to buy. So you're looking at something, I need to manufacture 10,000 or something per day. What do you need to do to bring it up to that level of 10,000, and how can I do it the cheapest and in the most efficient way? And simulations allow you to do that. And once again, it all depends on how good your model is. Another thing that simulations have been used for a while now is analysis of events which have already happened. You want to see what really happened, and if it happens again, can I deal with things in a better way? And this is a recreation of the 9/11 plane crash into the World Trade Center in the US. So they've used Google Maps as the visual environment. This is all the Google Maps thing, and they're modeling the plane actually going into the World Trade Center. And they model everything from the dispersion of fuel to the structural impact on the building, the struts. It just depends on how much detail you want to go to, how much detail you want to go into, and take it from there. This is another model of what would happen if this engine of this airplane suddenly caught fire. How would that fire disperse? So they're trying to come up with evacuation models, like if this happened to a plane while it's standing at the airport, how long do we have to get everybody out of the plane? So that allows you to set up safety regulations for how the plane goes. And then if you were to put this fire out, what's the best method to where you start from, what type of material you use, all that you can do if you have a good model, once again. Right? This is another interesting one, which is this is an analysis of the 2004 tsunami in Banda Aceh, which is in Indonesia. That was the first place that the tsunami hit. So this first recreation was actually what happened in real life, where the people only started to run away once the wave hit the shores, once they saw the wave coming. And what they've done is they tried to see, like, and from this you will find that of the 11,000 people who were there, but half the people actually died because they didn't have enough time to run away. And then soon after that, they were trying to decide, right, now we need to put tsunami warning beacons outside. So if you have to save as many people as possible, how far away should the tsunami warning beacons be? How much time do you need to give to people so that you can save as many of them as possible? So this is what actually happened. Where people started run away only after the water started to come in. As you can see, the water was like, after the earthquake, within 46 minutes or something, the water had already engulfed the whole city. And you can see 5,400 people. So under those circumstances, about half the people in the entire city actually died. So now they were trying to see how they can improve on that. So what they said was, what if the tsunami warning was given 10 minutes after the earthquake went off? And then we did a model on that to see how things would improve. So here, the warning to the people was given much earlier, which is 10 minutes after the earthquake, and they started to evacuate soon after that. Right? So you see that people are there, now they start to evacuate because the warning's already come in, it's 30 minutes after the earthquake. And the water still hasn't come in, but they've already started to evacuate. And with this, they found that with this model, only about 1,000 people out of the 11,000 would have actually died if they had this already in place at the time that the tsunami came in. Yeah. So you see, water hasn't even come in yet, but people have enough time. So once again, you've got to have a good crowd model to be able to do this properly. If not, you're just playing around in numbers, right? So it all depends on how good your model is. The first step with any simulation all is to have your model, and then you figure out ways to use that model once you have it. What comes in. And as you can see, most of the people have already evacuated. These orange spots are big high rises, so that could be set as evacuation zones. People go in and then climb up. And the rest of the people run away. And in this situation, we see 200 people have died out of the 11,000, whereas earlier, more than half the people. So this is all about planning, right? It's about once something happens, you analyze it to see how you can do it better. Then, now we go on to my field, which is training. There are companies develop simulations for training. And once again, simulations are now, the usage of simulations in training now is huge. And I'll give you a few examples. This is once again the crowd model. You have a city, and then these simulations are being used to train this guy who is a security guard who needs to watch all these CCTV cameras. And so he's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15 cameras. And by watching all 15 cameras at the same time, he's got to identify when there's a pickpocket in just one of them and then immediately call the police. But that requires training, right? Because you've got to be watching 15 things at once. So what a typical instructor would do is he would run a scenario. The instructor would be seated somewhere in the back. And then the instructor would have the chance to simulate a pickpocket here, somebody robbing somebody here, somebody robbing a store here, and that would allow the person to train. So once again, this depends on how good your city model or your crowd planning model was. And then you can make this more and more realistic training for this person who's trained to be a security guard. This system is used by, I know, the municipality of Toronto, Washington, New York. Lots of the big cities use systems like this to train their policemen and their security guards. Okay. Similarly, something similar to what we do, where another use of simulations is actually related to what we do, is where the trainee can actually participate in the simulation as a person in the simulation and actually interact with what's going on. It's like playing first person shooter games, where you actually walk around, do stuff, and then you can use the simulation to train them on what needs to be done. So this is a trainer for a firefighters, where once something happens, the firefighter is supposed to go somewhere, and then he'll give you instructions on what you should do. You pick up the post, you pick up the radio. So it's all procedural support like that. And the person using it can play it like a game. And this is used by a lot of the fire departments in the US. They have systems like this where they put in different scenarios and they just train them on what needs to be done when something happens. So you see, there are different options, where you call somebody, where you radio somebody. But trust me, these are not games. These are actually used by firefighters in the US over and over again, and they've been using them for the last 5-10 years. their cars and also to train people. So they're going to hand this over to the Japanese government or something. They can use this to test people, train people, even evaluate drivers on how to do things. This is once again a link between hardware and software. But even here, for this model in the background to be realistic, then you've got to have people walking around, you've got to have other vehicles driving around, and that all requires a model. If not, this training is not going to be accurate. Alright. And then is another example where air traffic controllers, at airports, the guys who control the planes up in the tower, they can be controlled how to control the planes, how to do instructions. So like this, there are now simulation-based trainers for almost everything, right? It's just a matter of how good your model is and how good the trainer is. Some trainers are not so good, some are very good. It just depends on how much time and effort was spent on building them. This, once again, flight simulator, so you can see a huge change from that first flight simulator in the 1920s, how much things have changed since then. And this is more related to what we do. We do a lot of work for military, but we also do non-military stuff. And part of the software used to build this simulator was actually built at our company. This is the next step in simulation technology, what's called fully immersive virtual training. Immersive means you're actually inside training environment. So the eventual target of the US government, NATO and all these guys, is, some of you must have seen Star Trek, where you have these holodecks where you go in and you interact with hologram characters. So like that, the eventual target is to go towards that. But the first step towards that is where all the soldiers are put in full bodysuits and given goggles. And then inside, through the goggles, they actually see the virtual environment. And they can walk around the room, pick up their guns, fire, and do all that. And they can go through an entire exercise just by walking around, moving. And I'll show an example. Some of the software used to build this was built at our company. I'll give you a bit more details on that. This is a project that the US Army has been working on for the last 3 years. It's called the Dismounted Soldier Training Program, where the soldiers are put these goggles and these bodysuits. This is the virtual environment, and then they can actually get into the scenario, walk around, play, just go through the entire mission, almost like they're actually there. And this is now being used by the US Army. They've been using this for a couple of years, about a year now. And the cool thing about this is that they built it to be portable, so that they can take it anywhere and set it up within, I think, 4 hours. They can set it up and do training even in the middle of a field somewhere. So even the weapons here, they look like real weapons. They don't fire, they are electronic weapons. And they are linked to the simulator directly, so you point direction fire, the simulator also fires, but they also have the hardware so that you get the kickback and everything like a normal gun. So they try to make it as realistic as they possibly can. And with this system they can rule 9 soldiers at once, which is really, really good. And the cool thing about an environment like this is you can set up a new training mission within like 5-10 minutes. If your system is good, you just create a few buildings, add a few things, and immediately the guys can go inside and start training. Alright, just to go back to a little bit more theory, just to show you how important simulations are now regarded around the world. I'm taking an example of the Australian Army, which is, I think, about 20,000 soldiers. The Sri Lankan, the entire Australian military, Army, Navy, Air Force is 20,000 soldiers. I think just the Sri Lankan Army is 300,000. So they're like less than 1/10 of the size of the Sri Lankan Army only. But still, this is how serious they take simulation. the whole simulation department is divided into, they have senior simulation appointment, 3-star general in charge of only simulations. They have what's called a defense simulation forum, where there are people who decide on the future direction of this thing. Then you have what's called Defense Science and Technology Organization, which does experiments and research. There are people who buy software from us or they give us contract work. Then you have the Defense Material Organization. They are the people who buy simulators, actual hardware simulators, like they run. So it's a big organization. And then if you look at the actual forces, the Army has battle simulation centers, combat training centers, land command centers, like that, the Navy, the Air Force. And just the amount of people controlling simulations in an army of, say, 20,000. We have, I think they have like 200 people full-time who are just involved in doing simulation-related stuff, in preparing simulation. That's how serious they take simulations. But the thing is, the question you will ask is, why aren't the Sri Lankan Army people doing that? The main reason for that is actually, it's because we are under the company, nothing else. That when you take an Australian soldier who joins the army when he's 18 years old or 19 years old, more often than not, that guy has already been playing computer games for about 10-15 years of his life. He's been playing PS3s, Xboxes, all that. And then the moment you give him a computer or an Xbox, controlling a character inside a game for him is almost natural. He doesn't have to think twice about it. Whereas, unfortunately, our guys, soldiers who have joined now, are not that proficient with computers. The moment you give them a simulator to train, they're more worried about making a mistake in the simulation rather than using the simulation to actually learn something. So in another 5 or 6 years' time, Sri Lanka will get to that level. But the reason that this is so successful in the US and UK and all these countries is that the soldiers who come in to join the army are extremely proficient. So when they're given a simulator to be trained on something, they don't need to concentrate on using the computer. They concentrate on actually learning something from the simulation itself. Yeah. Alright, so let's go to my company, SimCentry. Like I mentioned earlier, we are a R&D company based in Sri Lanka. We develop about 6 products. Up to now, we have lots of other sub-products based on that. So overall, we develop about, I think, about 15 or 16 products now. We do everything that we develop is developed by us. We do the research, we develop from scratch, so we own the IP of everything that we built up to this point. We are about 5 years old. We started in Sri Lanka about 4 years ago, but we initially started development of first software, myself and my partner, about 5 years ago. And then we started operations in Colombo in 2009, almost 4 years ago, with 3 people, and now we're up to about 90 people. We're very young staff. I think everybody other than myself is under 30. Yeah. And so we got all young staff, lots of people from Columbia University, Motor University, places like that. But of course, like I said, our focus is on developing simulation training software and what are called simulation add-ons, and I'll show you a couple of examples of that. We work primarily on a platform called VBS2. VBS2 is a simulation environment. It's like a graphical engine, which is almost like the standard for simulations around the world. That fully immersive training program that you saw earlier with the bodysuits and stuff, the visuals of that was all done with VBS2. So the US Army, US Marine Corps, Navy, UK Army, United Nations, WHO, UK MOD, Australia, New Zealand, Canada, France, Germany, all these guys own like thousands and thousands of licenses of VBS2, and they use VBS2 for training people on everything. So we are not in a stage where we could have built a simulator from scratch. So and to match something like VBS2. So what we do is we build software which runs inside VBS2. So I'll give you examples of that. So Bohemia Interactive, the company which builds VBS2, is a big company. They've been around for about 10 years now. And it's almost like the gold standard for simulations now and simulators. VBS2 is really amazing because it allows for network scenarios. You can have even 400 soldiers joining a single mission on 400 PCs. They can go through the entire mission, beginning to end, and practice it. It's got really good graphics. It runs on most PCs. I mean, one of the requirements for the US Army was that VBS2 needed to run on a laptop. And the main reason is they could be able to take a laptop into the field in the middle of a war situation and use it there as well. It is compatible with any disk simulator, so anything else you can plug into another helicopter simulator or that. And also you can develop scenarios, scenes, missions, everything really, really fast. This is just a small video on VBS2. You can quickly set up a mission. And then once you set up the mission, people can just get in, join in as one of the characters and do whatever you want. And the amount of flexibility, the amount of models, planes, helicopters, everything is huge. I mean, the reason that nobody else can now catch up with VBS2 is that because these militaries have now been using it for about 14 years, they have now developed all their cars, their people with guns, everything has been developed, and no other platform is even close to VBS2 in terms of having that much rich content. I know for a fact that the US Army, before they do most of the stuff that they've been doing in Afghanistan and Iraq, the soldiers actually practice the entire mission in VBS2 before they actually go and attack that village or whatever. So this is like the thing that they use for almost everything. Okay, so like I said, we as a company, we develop software which runs mainly on VBS2. We got 6 main products. One of our products is VBS2, I'll talk in a bit. We got 2 add-ons. 3 add-ons and 2 very, very specific training applications, which I'll show you quick demos on. So our first product is VBS2 Fusion, which is actually the official API for VBS2. So if anybody wants to link an external program or external hardware onto VBS2, they're going to use our API, and we have been developing this in Sri Lanka for the last 4 years. That fully immersive example that I showed you earlier with the bodysuits and the specs, using VBS2, all the hardware that you see in there is linked to VBS2 using VBS2 Fusion, which we build in-house. So like that, we have many clients around the world who are using VBS2 Fusion to link into VBS2, and even all the products that I'm showing now, which work on VBS2, have all been built using Fusion. We've been very lucky. We got this contract a long time ago, and we have a very close relationship with Bohemia Interactive, which does VBS2. And because we built Fusion, we actually build some of the best products for VBS2 than anybody else does. Right? So with Fusion, you can do almost anything inside VBS2 from outside. You can add people, delete people, control them, shoot. Whatever you can do in a normal game, you can do it outside programmatically with C++ using a program. You can get data out, you can draw things, anything. Then so this is just a very quick demo on Fusion. This is something that the Norwegian army has been working on, where they've been using Fusion to do training for, so all these drawing the maps, getting the data out for the maps, it's all done with Fusion. Another example of Fusion obviously was that earlier video I showed you. Now, one of our new products, which we've just launched over the last couple of months, is this product called Crowd Ambience, which is instant crowd generator for VBS2. So in VBS2, you can have cities, but then if you're running a training mission, you're driving around, or doing, or your troops are walking around or whatever, you still want the city to look alive. And what we've done with Crowd Ambience is a product which allows you to instantly generate crowds inside any VBS2 city. And I'll show you an example. Alright, so this is a demo of a Crowd Ambience feature. And like I said, the main thing about this was that we wanted a solution where people could generate crowds inside VBS2 cities really fast. And this is all to us that you have empty cities. And then with a couple of clicks, what you can do is you can add crowds, you can add people into the city. And those people will automatically, we suck a lot of information out of terrain. We generate the crossings, the sidewalks. You can create different types of people, different avatars. It integrates beautifully with VBS2, and also you can create, you can also set up different types of behavior. You can say that I want this person to follow the sidewalks, use crossings, or if not, I want certain people to just cross wherever they want. So very fast, people can create. So like this, the typical scenario where you're adding a certain type of civilian, I want 160 of them in a particular location. Add crowd. I can set how chaotic I want them to be, and then you click go, and immediately you have people appearing inside the VBS2 terrain. And the cool thing is that they look like real people. They follow sidewalks. They're not just walking around randomly. And the really difficult part of this was to create a program which will work on any map. Creating a program to run on one map is not hard. I can probably do it in a day or two. But to build something generic which will work on any map was always a challenge. And now we've got a really cool product, and this we just launched a couple of months ago, and people have just started buying it. So this is, once again, this is an add-on for VBS2. This on its own is not a training tool, but if you are running a training mission in VBS2, you're going to need this to create the background people running inside your mission. Right? So similarly, we've got another research project, which is the same thing but for traffic. It's another instant traffic generation tool for VBS2. We haven't launched this yet. We are just doing demos. We are on the final QA run. But this is once again an instant traffic generation tool for VBS2. And this, a lot of people are waiting for this. And once again, this is also highly configurable. Vehicles go on the correct side of the road, they overtake properly, they detect the width of the road, they know how they should behave at junctions. You can also have traffic lights. You can just instantly add vehicles to any VBS2 city and terrain. And these two combined, now any VBS2 user has a really good solution for just adding life to any VBS city, and that's the most important thing. For any simulation, for a simulation to be useful, it's got to be realistic, right? And if you're a soldier just walking around an empty city, it's much better to have a soldier walking around the city with people and vehicles, and that's what people want. All right? So similarly, you have a very simple program to build the cities, and then once you've got that, they follow the road rules, they follow junction rules, all that, all done automatically. And the cool thing is that our entire ambience program runs outside VBS2 as a separate EXE, a separate program. Inside VBS2, we just show the visuals. So it's all built externally outside VBS2 as an add-on, and we use VBS2 Fusion to just update locations inside. So the entire state of our traffic is maintained outside in a separate EXE. This too took us about 3 years to build, and we're still finalizing some final things, but it's looking quite good at the moment. All right, so traffic ambience. And then we go to one of our really old products. This was actually the first product that we built. It's called VBS2 Fires. Now, just to give a bit of background, this is a military-specific product, and this is a trainer for what are called forward observers. Now, if you know the big guns that are used in the military, the normal procedure is that these guns are about 20 kilometers away from where they're actually going to hit, 10 or 20 kilometers away. So what happens is one or many guys called forward observers, they would get as close to the place that they're going to bomb as possible in camouflage or whatever. And then he or she is supposed to radio back instructions to the gun on where to fire and all this stuff. There are very, very strict protocols on how these instructions should be given. And then once you fire once, you're obviously not going to hit the correct place, then you've got to send corrections and all that. And VBS2 Fires is an application for training this forward observer. And on some background, this VBS2 Fires, the US Army uses it, the Marine Corps uses it. In the US, they use it in all the artillery schools. In the UK, the Royal School of Artillery uses this as one of their primary training tools. And this is a product that we developed in Sri Lanka and have been maintaining for about 4.5 years, and is a product solely owned by us. I've got some examples of people using it. So this is just VBS2 Fires. We've got this panel which allows you to enter information in exactly the way that people would enter it. Once again, different countries have different protocols and how these commands are given. So we've got different ways of doing that. And once the instructions are given, all the AI which controls the gun firing, the calculations done by the gun, the trajectories, the explosions, it's all done by our own AI. So this is all about the trainee would give instructions, and our program would take that over and then handle all the AI from taking the bullet all the way to the target. And that allows the trainee to just sit down in front of a computer and train on basically figure out how things should be done. This is a US Marine Corps example of the guys using our software in one of the mission bases. So here what they do is, these are some troops who have come home from Iraq after a year of service or whatever, and all the equipment has been sent for cleaning and maintenance and all that. So they've got about 2 months where none of the equipment is available, but they still want to keep training. So what they do is they rehearse everything that they would normally do with guns using VBS2 Fires, because their guns they don't have access to their guns. So they can basically practice everything that they would normally do with their big guns here. And then another thing that these guys are doing is when the forward observer sends out the instruction, they use VBS2 Fires, which is our application you see on the video here. They use VBS2 Fires to initially put the command into VBS2 Fires, see where the missile is going to land. If it looks all right, then they send the instructions over to the actual guns, which are then fired with the same instructions. Once again, this is all simulations, right? This is once again a product that took us a long time to build, but now people have been using it for 3+ years and using it quite successfully. The US Marine Corps, the US Army uses this quite a lot. And then another one of our newer products, which is an extension of EBS2 files. So the alternative to the big guns are airplanes coming and bombing. So similarly, if you want an airplane to come and bomb something, more often than not, there's what's called, instead of a forward observer, there's somebody called a forward aircraft control. The guy's got to go and hide somewhere in camouflage and all that, then relay back instructions to the plane. And planes are much more complicated because you've got to give more instructions. You've got to tell the plane where to come in, what height to come in, what type of explosive to use, whether you can get there, and then once you do the bombing, where you should go out, the direction you should go, the height. So all those, the guy in front has to make that full evaluation and make all the decisions and send information back to the plane, and then the pilot would just follow things and go and do it. So EBS2 Strike is an application for training that forward aircraft control. This we built under contract for the US Marine Corps, and the US Marine Corps has been using this for more than a year now, but now we are just about to commercialize it and sell it to the wider market within the next year or so. This is Strike. Like I said, we model everything from actually taking the airplane to the location, the AI, the path planning, everything is done by us, and then the trajectory calculation of the missiles, it's all calculated by us. So we get the instructions from the training, and then we have to translate those instructions into actual actions, and we have to do our own AI to follow those actions. So we handle airports, aircraft, helicopters, all that. This is all our AI controlling the trajectory of the airplane. And this is VBS2, right? We didn't write these graphics. Ours is a program which runs on the background, which is just an engine, which is controlling the orientation. Through Fusion, we send commands into VBS2 saying, I want the plane to be here with this orientation. So all the AI is outside, and we're just using VBS2 as an image generator. So these graphics are not ours, but the actual actions happening are all software that we wrote. Including these particle effects, the explosion, all that be done by us. Okay, so that's a quick overview of my company and the stuff that we do. So like I said, we have about 6 or 7 products, and similarly for Strike files, we have APIs where people can link hardware. So altogether we have about 20 products, but these are the 6 main products that we build. Right, and like I said, all these were developed in Sri Lanka by guys like you who had left university. And we develop, maintain, research all these items just on the road in Kolkata. Okay. So next thing is what I'm going to finish off with is, if you were to build your own simulation, what would you have to do? What are the things you need to do? Now, the main rule of thumb with simulations is that you should never try to do something that somebody has already done better. Because to build a simulation to a certain level takes a long time. And if you are starting from scratch and you're trying to catch up with somebody, by the time you caught up, that person has already done something better. So if somebody has already done something well, there's very rarely the need for you to try and do it again. So basically what you would do is you take what's available and see what you can do to add to it or improve on it. Just trying to do something that somebody has already done is not going to be worthwhile, because the thing about simulations is that simulations have to be effective. They have to be useful for whoever is using them. And if you're just doing something for show to say, I can do this, then the whole purpose of the exercise is lost. Right? So, if you were to build a simulation, what are the main components that you need? You need visualization. You need a graphics engine of some sort. You need models. The models in these terms are the airplanes, the buildings, the actual ground. If you want to do Colombo, then somebody needs to build Colombo for you in AutoCAD or whatever, right? Then you need background AI and behaviors, the stuff which happens on the background, which are not directly linked to the simulation, but are still important to make it more realistic, like what we do with crowded means and this thing. And then the more simulation-specific behaviors and models, like what we do in Fires and Strike. We do Fires and Strike, where we have our own ballistic models to calculate the trajectory of the missiles and all that. Those are the most specific models. So usually, if you were to build your own simulation, you wouldn't try to do these two, right? Because you just wouldn't be able to do anything good enough. So you would take something that's already there and try to leverage that. Then, so for example, if you were to build your own simulation, what are the options you have? So there are lots and lots of simulation engines out there. VBS2, what we use, we have CryEngine, we have the Vision Engine, then there are some open source ones like Delta 3D, Ogre, visual engines like that, which you should use. Never try to build one of those yourself. Then models. Once again, if somebody has already built a model, then usually there is not much use of you trying to build that model yourself. Or the only reason you would probably build it yourself is if getting that model from that person is very expensive, then you would build that much. If you want a typical Colombo building or even this building, if nobody else has built it, then you build it. If not, if somebody has already built it, then it usually makes more sense to pay some money and buy it from that person. And then the final model is the terrain. Now, terrain is a hard one. To actually build the terrain from scratch is close to impossible. Right? You've got to build the actual ground, you've got to have buildings, and that takes a lot of time. So what usually people do is they use something like a satellite image and what's called a height map. This you can usually download on the web for most areas, which is the height of the ground in different locations of the world. You can link those two together and immediately write a program to auto-generate the terrain. And then into that, you then add your buildings. Now buildings, you can build your own buildings, or if somebody has already built stuff, like I said, you can bring them in and that's how you would build your city. But if you were to build a city from scratch, and that's part of your simulation model, you will spend about 90% of your time building the city rather than spending time on the simulation. So you reuse as much as you can. Okay, and then what else do you need? You need graphics, like I said. You need a really, really good physics engine. That's one of the most important things. If your physics engine is not good, then your simulation might not be as good as you need it to be. You can build, if your physics you need are very specific, then you can maybe write some of it on your own. But building larger ones like Gaussian models and stuff, you're not going to get very far if you do it yourself, unless you're willing to spend 2-3 years bringing something up to a very, 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 very good standard. You need sound, you need some sort of scripting support, you need animations, the guy is walking around, you need some AI, and if you're going to do distributed missions, you need some networking as well. So if you want to build your own simulation, it's about figuring out what you need to do, and then describe the components you need, and then find out what you need to build yourself, what can you reuse from what other people have done, put it together, and then what are the most specific components that I need to write. And that's always a decision you need to make. Never start and say, I need to build this from scratch, you won't get anywhere, or nobody else is going to use it. Okay? Yeah. So now the direction that simulations are heading in now is that what the biggest drawback with simulations up to this point was that you either need very, very specialized people to build the simulation, also you need specialized people to maintain and run the simulation. Now that for most companies are getting smaller and smaller in the world now. Very few companies have 1,000, 2,000, 3,000 people. Most typical companies around the world now have about 100 people. And what they look for is to be able to run a simulation cheap. Now let's say you're an architecture firm and you're a team of architects and you want to decide whether your building is safe. Now, if you did that 10 years ago, we'd have to hire somebody like me or somebody with mathematical background, ask him to build a evacuation model, and after about 2 months, I'll come back to you with a good evacuation model. But now what people need is, where you're an architect, you have your AutoCAD model of that, you can directly plug it into a program, press a button, and immediately do a full evaluation, and it will come out with a printout at the end saying, how safe is your building. Now, this is what the customers in the world are looking for. They look for out-of-the-box solutions that you don't need any special training to be able to do it very, very fast. Now, if you build a system where you need to spend 1 month or 2 months configuring it, then it's only you who's only going to use it. If you're building a commercial product, any commercial product you has to be very, very usable. Because if you target things towards technical people, then most of the companies that you try to sell to will not have technical people in their staff to be able to handle those. So anything that you build has to be something that runs out of the box. Okay, and so what the main need, like what we're doing with Cloudem is you need reusable models, stuff that you can be used across a wide variety of simulations, and then just fill in the gaps. Like I said, just build what you need to build. Okay, so the current requirement is any organization that you're building this thing, they should be able to build a simulation, test something out. Let's say you're mayor of Colombo and you want to see whether making Gaul Road 2 ways again, is it going to improve things or this thing? No. They're not going to wait 2 years till Motor University does a project on it and come back straight. They want to be able to quickly load the model, within a day or two run several simulations and see what's the best option. Now for that, there is no software like that available anywhere. So it means any decision they make is decisions based on what are called experts, or they just come out of an idea out of the box. So the ideal solution would be Mayor of Colombo has a simulation, he has roads, he tries a few things, change this road to one way, that road, and see how things work. Does it improve traffic? Does it make things better? Things like that. So you should be able to do it quickly. Just be realistic. If it doesn't portray what happens in the real world, then it's not of any use. Then it just becomes like a game, right? You should be able to do it anywhere. You should be able to take it anywhere. You shouldn't have to have a computer this size, with a room this size, just to be able to do those type of simulations. And like I said, with minimal training and cost. The user interface is crucial if you are building simulations for the wider market. If you are building for specific organizations, then they might be able to hire people and have the money to do that only. But most companies don't have that money. So you're building stuff for anybody to use. And that's it. Questions? Yes, so I know it was a long talk, lots of information, but does anybody have any questions? Feel free, right? Don't worry about asking stupid questions or anything like that. I'm willing to answer.
To do the simulations, what kind of a background do you need to start?
Well, all our coding is done with C++. It's all done with C++ on Visual Studio. All our programs are Windows based. So VBS2 is a platform which only runs on VBS2. Oh, sorry, on Windows. It only runs on Windows. So all our programming is done with C++. I mean, normally you would need a pretty decent background in maths.
How much decent?
Depends on what you want to do. I mean, it really depends on the complexity of what you really want to do. Some you really don't need much. Some ones you need differentiation, integration. It just depends on the complexity of the task that you're trying to do. But the more maths you know, the better. But it's not a risk because a lot of this code that you need can be from somewhere else as well. If you want to write some complex maths code and you don't know how to write it yourself, more often than not you can find it somewhere on the web as well. So it's a matter, I mean, building this stuff is just putting stuff together. And some physics helps. Physics and statistics is quite important because you've got to come up with random generation models, especially for this. Our guys walking around and stuff, you need lots of statistical models to control the movements. But once again, if you have an understanding of what needs to go in, finding the code that you need to build something is not that hard because somebody usually has written it somewhere. Yes?
So if I want to configure that in my machine, so what would be the minimum requirement for that? I mean,
What
not
configure? VBS2.
Not any other.
Well, all our programs and VBS2 are usually built to run on more standard laptops. Usual requirement is having a decent graphics card. That's usually the only limitation. Other than that, I mean, the main requirement is when the US Army purchased VBS2, their requirement was that US Army gives laptops to all their colonels and captains and all these guys. As a standard laptop which they use and they update every 2 years. VBS2 has to run on that laptop. And that was always a requirement. And with simulations, one of the main things is what's called frame rate. Frame rate is the refresh rate of the simulation. And they wanted frame rates of at least 30 when VBS2 runs on those laptops. So VBS2 was built to run on laptops because they wanted to be able to run simulations in the field. So for our programs, you don't need huge computers. Most laptops can run them as long as you have a not so bad graphics card.
What about developing? I mean, if I want to develop using a Crytek or Unreal platform?
Normally, all you need is a normal PC. You don't need anything complex. I mean, for compiling, I mean, it might take slightly longer to compile, but for actually writing code, I mean, I've written code for VBS to on a notepad. I could run it on the notepad. But I've written code. So actually writing code and compiling, you can write it on anything which runs Visual Studio. And that's about it. I mean, I wrote one plugin on a small notepad. I wrote one on a tablet as well. You can't run it, but it's for writing, all you need is Visual Studio. Okay? Anything else? Feel free to ask questions. All right. Okay, guys. So thank you, and website for our company is simct.com. www.simct.com. You can see demos and stuff of all the software there if you're interested. Or I think Zaman has my email, so drop me an email if you guys have any questions. Okay, so thank you very much.
Thank you very much, Dr. Ramesh, for interesting presentation, and this is the end of our presentation.